Here's the thing. You've probably heard a version of this claim before. Quantum mechanics proves we create reality just by observing it. It sounds almost mystical, doesn't it? Like your thoughts or your awareness alone could control the fabric of existence. But what if I told you that idea is completely wrong? Hi, I'm Oli, a lifelong physics enthusiast, and today we're going to break down exactly what the observer effect is, and more importantly, what it isn't. I promise, by the end of this video, you'll have a much clearer and deeper understanding. And hey, if you love cutting through pop sci myths, subscribe to Hyperfocus, where we dig far beyond the surface of the universe every single time. Now, let's start with where the confusion comes from. The observer effect is often tied to quantum mechanics and typically gets dragged into two specific experiments, the double-slit experiment and Schrödinger's cat. So let's talk about the famous double-slit experiment first, because this is where it all begins. Picture this. You've got a device shooting tiny particles, like electrons, one at a time toward a barrier. This barrier has two narrow slits, with a detection screen placed behind it to capture where the particles land. If the electrons behaved only as solid particles, you'd expect them to form two bands on the screen, matching the positions of the slits, right? But surprise, when no one's watching, or to put it more accurately, when you're not measuring which slit the particles go through, they form an interference pattern, as though each electron behaves like a wave passing through both slits simultaneously. The moment you introduce a measurement to detect which slit it goes through, the interference pattern disappears, and instead, you see a two-band pattern consistent with classical particles. This is where people say something like, "Aha! The act of observation collapses the wave function, and reality changes purely because someone's watching." But let's pause and think about that. What does observation really mean in this context? It doesn't mean you need a human eyeball staring at the apparatus or your brain in the mix. It means there's a measurement device interacting with the system. That's a key point, and it's physics, not metaphysics. Quantum mechanics doesn't say the universe cares whether you're there to look at it. It only says the universe behaves differently when we force it to reveal certain properties. Measuring which slit the electron goes through, that's us poking the system, demanding an answer to the particle or wave question. And the act of measurement forces the system into one state or another. That's not the universe bending to the power of your gaze. It's the universe responding to an interaction, like a scale responding when you step on it. Think about this. Has anyone ever claimed that weighing yourself on a bathroom scale means your weight doesn't exist until you see the number? Of course not. Yet somehow, the same logic gets applied to quantum physics, and people eat it up like it's gospel. But wait, there's more. A lot of this misunderstanding also comes from Schrödinger's cat, that infamous thought experiment where a cat in a box is both alive and dead until you open it. Now, Erwin Schrödinger didn't come up with this idea to blow your mind for fun. He actually created it as a critique of quantum mechanics interpretations. In simple terms, he wanted to highlight how absurd it would be to take quantum rules designed for particles and apply them directly to large objects, like a cat. Contrary to how it's often presented, Schrödinger wasn't describing a literal reality where your observation determines life or death. Instead, he was illustrating the limits of our understanding of when quantum principles stop applying and classical principles take over. Unfortunately, this nuance gets lost, and the quantum mystics of the world twist it into claims that your mind can control the material world. It cannot. And look, I get why the misconception is attractive. The idea of humans being at the center of reality, able to influence it just by looking or thinking, is intoxicating. It makes us feel powerful in a universe that often seems indifferent. But that's just not what the science says. So why does this happen? Why does the observer effect get mystified? Part of the problem is communication. Jargon gets simplified for public consumption, which is fine. It has to be. But some concepts lose their precision along the way. For example, in quantum mechanics, the word observer doesn't mean a person. It refers to any interaction with a measuring device or apparatus that extracts information from a quantum system. A detector, a beam splitter, a photon receiver. These are observers, scientifically speaking. And I think it's important to emphasize the difference between observation and consciousness. Measuring a system and collapsing its probabilities doesn't require human awareness. You could set up an automated experiment in a vacuum, and the results would still demonstrate all the hallmarks of quantum mechanics. No people involved. All right, let's push a little deeper here. Why does measurement change the behavior of a quantum system at all? And this is where the real magic, and I do mean actual scientific magic, comes in. When we measure something in the quantum world, we force the system to interact with the classical world. It's like trying to snap a photo of a wild animal, except here, the act of taking the picture changes the animal's behavior. Before measurement, quantum objects like electrons exist in a superposition state, which means they're spread out across all possible states at once, described by a mathematical wave function. But the instant you measure, you codify its position, momentum, or path. And here's what's wild. This isn't just a particle thing. It happens universally. Superposition allows quantum mechanics to work the way it does, and is why phenomena like quantum computers exist. These computers exploit the ability of quantum systems to hold numerous calculations simultaneously before a measurement forces them to decide. So, what are the implications? If human observers aren't the linchpin of reality, does it mean we're irrelevant to the cosmos? Hardly. It means we're part of a fantastically intricate system that follows its own rules. The observer effect is, fundamentally, about connections. How measuring one part of nature influences another, and how those influences ripple across our understanding of the world. Let's consider the practical applications. Quantum mechanics underpins much of modern technology, from semiconductors to lasers to quantum encryption. These breakthroughs don't rely on whims or mysticism. They rely on predictable, rigorous measurements. Every laser in a checkout scanner, every transistor in your phone, embodies laws of quantum interactions. Yet nobody claims their phones function because they casually glanced at them, right? Here's another way to think about it. Imagine a symphony orchestra. The musicians represent particles, each playing their role. Measuring one is like striking up a solo performance. It alters the dynamics of the broader ensemble. It's beautiful, complex, and deeply interconnected, but it doesn't require an audience clapping in the seats to make the music real. All right, I want to leave you with this. The real wonder of the observer effect lies not in the idea that we control reality, but in the deeper realization that we live in a universe that's participatory, where observation and interaction transform possibilities into outcomes. It's humbling and thrilling at the same time. So now that we've unraveled one of the most persistent quantum mechanics myths, tell me, did this change how you think about reality? Do you feel less powerful or more curious? Let's discuss in the comments. And if you want more meticulously deep dives into physics that don't compromise on the truth, hit that subscribe button. Together, we'll hyperfocus our way through the universe's most fascinating mysteries. Stay hyper-focused and observe reality wisely.